Quantum mechanics rests on a non-negotiable rule called unitarity. Quantum information can never be destroyed, but the black hole information paradox is a strict mathematical contradiction that forces a violation of this rule. In 1975, Stephen Hawking formulated a proof demonstrating that when a black hole evaporates, the information contained inside is permanently lost to the universe. Hawking modeled the event horizon as empty spacetime, a dataless vacuum represented by the zero state. Virtual particle pairs spontaneously form here. One falls inward while the other escapes outward as a featureless thermal wave, carrying no data. If the horizon is truly a pure vacuum, the escaping radiation is entangled with nothing, unitarity breaks, and information is erased. Semi-classical gravity, the framework Hawking used, relies heavily on an embedded assumption that the effects of quantum gravity are extremely small. Physicists traditionally assume quantum gravity takes over only at the Planck length, a microscopic scale exponentially smaller than an atom. Compare that to the macroscopic scale of a black hole's Schwarzschild radius. The event horizon is vastly larger. Because the horizon is so much larger than the Planck length, semi-classical gravity assumes quantum effects cannot possibly reach the surface to save the information. To preserve quantum mechanics, we cannot rely on tiny corrections deep at the singularity. We must prove that order unity quantum effects physically scale up to the macroscopic size of the event horizon. We can test this by examining the two-charge extremal black hole, the simplest testing environment for this problem within string theory. The theoretical setup involves compactifying 10-dimensional string theory down to lower dimensions by wrapping strings and momentum around a hidden compact circle. This animation shows what classical general relativity predicts for the geometry of this hole. The spacetime pinches downward into a smooth, infinitely long, narrow tube. Classical math dictates that this infinite throat eventually ends at a traditional event horizon, with a singularity trapped deep inside. This classical infinite throat is the exact location where the dataless vacuum hides, guaranteeing the loss of information. To find the true geometry, we abandon the classical approximation and calculate the specific quantum microstates of the hole using a configuration called the D1-D5 system. In this system, we can observe the behavior of a single string carrying momentum by vibrating in a highly specific profile. This visual maps the baseline oscillation pattern. The string winds around the compact space in a uniform helical sequence. In string theory, the mass and vibration of this string do not sit passively. It physically warps the space around it, creating its own local geometry. As the string oscillations compound, the compact circle fibers non-trivially over the non-compact directions. This structural interference prevents the space from pinching into a singularity. The resulting topology is an abrupt, highly complex boundary, rather than an endless drop. The throat is capped. Calculating the precise string microstates reveals that they physically cap the throat, replacing the infinite drop predicted by the classical model. How do microscopic string vibrations affect the macroscopic boundary of an event horizon? The transverse amplitude, the physical width of the string vibrations, is dictated by the occupation number, which tracks how many quanta share the same harmonic state. Look at this scaling effect. By lowering the energy frequency of the vibrations and increasing the occupation number, the physical size of the quantum state physically inflates. We can measure this against the Bekenstein-Wald entropy equation, which calculates the strict thermodynamic boundary size of a black hole. When we compare the calculated surface area of these inflated string vibrations to the macroscopic entropy calculation, the two values match. Quantum gravity effects naturally scale to the size of the Schwarzschild radius. The assumption that quantum mechanics is confined to the Planck length is incorrect. We can now physically redefine the event horizon as the macroscopic boundary of a massive, fuzzy quantum structure. The mathematical representation of this new boundary is defined as a specific data-rich quantum state known as psi. This split screen contrasts the two models. On the left is the pure vacuum zero state. On the right, the tangled string cap, state psi. The equation makes clear that these states are mutually exclusive. It breaks Hawking's original requirement for his proof. When virtual particle pairs are produced at this data-rich boundary, the escaping particle interacts with the complex tangles of the cap before it radiates outward. Because the local state is not a vacuum, the outgoing Hawking radiation is physically imprinted with the data of the constituent strings. Unitarity is mathematically restored. If the horizon is a dense web of strings, what does an infalling observer or particle actually experience? Why does general relativity still seem to apply? We must separate the physics into two distinct timescales, the crossing timescale and the evaporation timescale. This diagram shows the crossing timescale. It represents the rapid, immediate plunge of a heavy object. Over this incredibly short crossing time, the fuzzball absorbs the high-energy object effectively like a classical vacuum horizon. The immediate physics perfectly matches general relativity. The dynamics change completely on the evaporation timescale, a timeline exponentially longer, where the information paradox actually occurs. Over this longer timescale, an infalling quantum behaves differently. It fractures and becomes trapped in the complex phase space of the cap, bouncing endlessly across the component strings. The horizon acts as a classical point of no return only for short times. Over the lifespan of the black hole, it functions as a highly complex quantum trap. The trapped quantum data cannot remain in the fuzzball forever. The structure is inherently unstable and must eventually radiate. This happens through a process called ergo-region emission, where the rapidly rotating quantum geometry physically forces radiation outward. This animation shows ergo-region emission. As the radiation pulses outward, it carries the exact structural data of the cap away from the black hole. This slow leak of geometric data is Hawking radiation. The long-term radiation is fully entangled with the initial matter that formed the hole. The black hole information paradox is resolved. The event horizon is a mathematical artifact. By inflating quantum string microstates to macroscopic scales, the universe actively prevents singularities, ensuring no information is ever lost.